chemical evolution in star formation and how to link it to the solar system. As you heard several times today, the star formation process is the formation process of a planet system like our solar system, and sun-like stars formed by the gravitational collapse of a dense molecular core, which have the mass of several solar mass and the size of 1.1 parsec. In this talk, I'll introduce the accretion process in low-mass star formation, and I'll introduce my chemodynamical model to calculate the chemical evolution in the collapsing core, and I will link the result to understand the environment of solar system formation. The standard model for low-mass star formation was developed by Frank Hsu in 1977. According to his solution, the singular isothermal sphere is gravitationally unstable to collapse. In the process, the accretion rate is constant and proportional to the cube of the sound speed in the gas. If you see this movie for the evolution of density in the collapsing core, the collapse begins from center and move outward. So we call this inside-out collapse model. It is a simple solution, can provide the density and velocity profiles with the time. If we adopt this standard accretion model to calculate the luminosity of a protostar with a 0.08 solar mass, which is the boundary between stars and brown dwarf, it gives 1.6 solar luminosity. However, observations by infrared space telescopes revealed that the majority of protostars have a luminosity lower than this 1.6 solar mass solar luminosity, and it has been known as a luminosity problem. One solution for the luminosity problem is episodic accretion, in which material piles on a disk until gravitational instabilities drive mass inward in short-lived bursts, as detected in FU Orionis object. And therefore, most of the mass accretes in a small fraction of the protostellar lifetime, and thus the protostars stay at low luminosity except accretion burst. Let's move to the chemical change responding to the dynamical process. In prestellar cores, the only heating source of this dense molecular core is the external interstellar radiation field. Therefore, the temperature decreases from the core boundary to the center. So at the center, it is cold center, most molecules are frozen onto grain surfaces as ices. However, once the collapse starts, the accretion to the protostar hits the surrounding material. So at the center, molecules can evaporate from dust grains to the gas, and the complex molecules can form on grain surfaces in this pre-stellar stage. So once the collapse begins, the complex organic molecule can be detected in this hot region at the core center. To calculate chemical evolution in a collapsing core more quantitatively, I developed the chemodynamical model. This slide describes how my model is composed. Oh, I'm sorry. First, I adapted the Hsu's collapse model for dynamics and derived the dust temperature, gas temperature by solving the continuum radiative transfer and gas energetics. And then I calculated the chemical evolution by following infalling gas particles and later converted them into the abundance profiles with time. To compare with the observation, I calculated the line radiative transfer and simulated the line profiles. In this model, one important parameter is the luminosity evolution. In Hsu's model, in continuous accretion model, the luminosity increases very smoothly, but in the episodic accretion, the burst accretion features appeared like this. This movie shows the chemical evolution in the gas phase, in a collapsing core. In the early phase, the core still is very cold, so all molecules are frozen onto grain surfaces, but the core is heated up. The gas can evaporate from grain surfaces to the gas. But in the episodic accretion, the chemical evolution must be different because the temperature evolution is very different from what expected in the continuous accretion. So let's look at this CO molecule, which is the most abundant molecule in the ISM, except for H2. This slide compares the CO abundances and emission distribution in two accretion processes. If we, in the continuous accretion, this current very low protostellar luminosity tells you this core is really cold, and almost all CO is frozen onto grain surfaces like this. But the episodic accretion, the previous, although the current luminosity is very low, the previous accretion, burst accretion, hits this core to the large radii, evaporate the CO. Even after this burst accretion ends and the material cools down, CO stays in the gas for a long time because the CO freeze-out timescale is order of 100,000 years in this density. So you can see very big CO emission radius. Actually, Jens Jorgensen found that the CO emission radius of protostella, several protostars, are generally bigger than what expected from their current luminosity. These red dots indicate the CO emission radii derived from observation in 16 protostars, and this solid line indicates the CO emission radii calculated from their current luminosity is in the assumption of continuous accretion. So this result could be a strong evidence of episodic accretion. I would like to give a quick summary of the chemical structure of a protoplanetary disk with this slide. You already seen these figures several times. This disk is heated mainly by the central source. The matter close to the center and the surface is hot, but getting colder downward and outward. So in the disk midplane, most molecules are frozen on grain surfaces as ice is. However, in the hot surfaces, molecules are dissociated to atoms by this high energy UV photons. And in the disk, grain particles can grow and settle down to the midplane, and so small grains can be lifted by turbulence, but big grains drift inward because of the velocity difference between grain and gas. So based on our knowledge on this chemical evolution in star formation, the relative chemical composition of planets, comets, and asteroids can provide indirect clues to the environment and processes that existed operated in the formation of the solar system. And three important chemical composition in the solar system are the first, high D to H ratio in comet, meteorite, and IDPs, and the second, the carbon deficiency in the Earth and asteroid, and finally, the oxygen isotope anomalies measured from the primitive meteorite. I will introduce quickly my work on these two first topics, but I will focus on the third one in this talk. The cosmic interstellar D to H ratio in H2 is about 3 times 10 to the minus 5, which sets the initial condition of a molecular cloud. And Protosun and Jupiter, which represent the gas in the early solar nebula, have a similar D to H ratio to that of the interstellar medium. However, in the comet, meteorite, and IDPs these have a very high D to H ratio. In addition, the interstellar molecules, including water vapor, have extremely enhanced the deuterium enhancement. In low temperatures, in a molecule, H atom can be replaced by D atom because it's a lower ground energy level. So the deuterium fractionation of H3 molecule and following the dissociative recombination of H2 plus can increase the relative abundance of deuterium atoms in the gas, as seen in this solid line here, the gray solid line, and resulting in the high concentration of deuterated water in grain surfaces. And the D to H ratio of water ice quickly drops with the temperature. Therefore, the sun must form in the cold gas to have ices with high D to H ratios. This figure describes the dramatic gradient in the amount of carbon relative to silicon incorporated into the Earth, meteorite, and comet. Unlike a comet, the Earth has 3 orders of magnitude less carbon compared to the interstellar values. And moreover, the carbonaceous meteorite shows this carbon deficiency too. However, comet doesn't show any carbon deficiency compared to the solar value. Therefore, in order to destroy this carbon grain, the primordial carbon grain, we need this mechanism. And according to our calculation, the primordial carbon grains can be destroyed by oxidation and photochemical processes in the hot disk surfaces. And the efficiency of this destruction is decreasing within the asteroid belt and is inactive in the cometary formation zone. From now, I focus on the oxygen isotopes. In 1973, Clayton et al. Discovered that the calcium aluminum rich inclusions, so-called CAIs, in primitive meteorite had anomalous oxygen isotopic ratios. This figure shows the relation among 3 oxygen isotopes. Here, delta 17O and delta 18O are defined by this equation. And the standard for these delta values is standard mean ocean water. And H symbols indicate the measurement from various rocks. Rocks in the Earth and Mars follow this slope of line, but measurement from CAIs follow a different slope of line. And according to the Genesis result, solar values is about -50 per mil, which is very similar to the highest anomalies measured from primitive meteorite. And this terrestrial line can be explained by the mass-dependent chemical fractionation, but this anomalous meteoric line requires a mass-independent chemical process. One mass-independent chemical process in ISM is the CO photodissociation. This slide shows the isotopic selective photodissociation effect. CO photodissociation occurs via a line process, and self-shielding depends on the column density. So at the visual extinction less than 0.5, all isotopes are photodissociated, but at the visual extinction between 0.5 and two magnitude. C16O is self-shielded, but C18O is photodissociated. So, and 18O atoms is frozen onto grain surfaces to make water ice enriched in heavy isotopes. But at the visual extinction greater than 2, all COs are self-shielded. We used our chemodynamical model to calculate the evolution of oxygen isotopic anomalies in collapsing cores by including CO fractionation and isotopic selective photodissociation, and try to answer two questions. What level of rare isotope enrichment is provided to the disk, and what is provided to the sun? This figure shows the result from several models with different G0 values here. Before collapse and 4.6 times 10 to the 5th years after collapse. G0 is a measurement of the strength of local far UV radiation field relative to the standard interstellar radiation field. And photodissociation rates are scaled by this G0. So as expected, before collapse, in most cases, the highest anomalies is imprinted at, observed toward the core boundary. And after collapse, these high anomalies can move with the material. In this calculation, we assumed the material in the boundary of, inner boundary of collapsing core is provided directly to the disk. And we also assume the significant grain growth and grain settling in the disk has occurred. And thus, material fractionation between gas and dust, which is caused by the drift inward of solid bodies relative to gas, has also occurred. So, because of this material fractionation, our disk is enriched in C16O, but in the inner disk is enriched in H218O and H217O. So water vapors are enriched in this region. So this material fractionation also affects the solar oxygen isotopic ratios and solar C2O ratios, so we can constrain the time when this material fractionation starts. These two plots shows the variation of solar C2O ratio and solar delta 18O values with the time when the material fractionation started. So, according to our calculation, if about 7% of solar mass is affected by this material fractionation, these two solar values can be fitted under G0 of 100,000 and 100,000. As the heavy oxygen isotopes are enriched in water ice, they are very deficient from CO gas. And in the outer nebula, where comets formed, okay, in the outer nebula, CO gas is enhanced, and the CO molecule is very deficient in the heavy atomic oxygens. But we detected very high oxygen isotopic ratios in meteorite and comet. So we need a continuous source to compensate the low oxygen isotopic ratio detected in C16O, CO vapor. So we need a continuous source for the water ice with the very high oxygen isotopic ratios. This plot shows the oxygen isotopic anomalies. provided to the outer boundary of the solar nebula with the time after when the mass of a protosun reached the 1 solar mass. So among 3 models that fitted the solar values, only one model with the GNAT of 10 to the 5th can provide these high oxygen anomalies to the outer solar nebula. So therefore, we need to explain these oxygen isotopic anomalies detected in meteorite and comets. We need a very high UV radiation field. This high GNAT value is supported by the presence of 60 ion inferred in meteorite, which is provided by a type 2 supernova. Therefore, we suggest oxygen isotopes provide independent supporting evidence for the presence of a massive O-star near the forming sun 1 million years before collapse. This is the conclusion, my conclusion. So our advanced knowledge for the chemical evolution in star formation can be applied to understand the formation environment of the solar system. However, for more realistic studies, we needed to improve the thermodynamical model by including grain growth and segregation between gas and grain in the disk, and the surface chemistry for more complex molecules, and the effect of episodic accretion. Okay, thank you.
Thank you, Daniel.